Right, here's just another example. I'm going to keep working through them. Oh, this page broke very poorly. There's space at the top of the next page to do this. Mass M1 is resting on an inclined plane with coefficient of static friction, US. String connected to the mass runs over a pulley at the top of the incline and is attached to hanging mass M2. Angle of incline is theta. Find the minimum value of M2 such that the masses will begin to move. So what's going on here is we've got an inclined plane. Mass is sitting on the inclined plane. We got a pulley, string, hanging mass. Hanging mass is M2. Sitting mass is M1. Right. Inclined at angle theta. And we have a coefficient of friction, mu s. So we want them to just barely begin moving. Well, just barely begins moving means that net force is 0. So technically it's not quite 0, but it's negligibly small. So for M1, we know we have gravitation, we have normal force, we have tension, and then we're going to have friction. If it starts moving, that means that M2 is going down. Well, probably. I guess we would have to say, we should say mass 2 is greater than mass 1, because otherwise we wouldn't know for sure. Mass 2 is greater than mass 1, then it's going to tend to, M2 is going to tend to go down, which means M1 will tend to go up the ramp. So then we have static friction acting down the ramp. For M2, we have gravitation, and we have tension. And this is going to be the same tension that's in the rope over there, because it's the same rope. Oh, zoom a little bit. A little bit more. All right. So we need to write equations for each of our blocks, but we need to be consistent about our directions. That's the key thing here. So for M1, in the direction perpendicular to the ramp, we have the thing that's kind of usual. For ramps, normal force is equal to mg cosine theta. Now, in the x direction for M1, this is all for M1. So in the x direction for M1, up the ramp we have tension, and down the ramp we have a component of gravity and static friction. Now we want it to just barely start moving, which means we have the maximum static friction. The maximum static friction is being overcome. So we get this. For M2, you can write the equation. But the thing is that M2 moving up and down corresponds to M1 moving up and down the ramp. Okay, so we need to be careful about this. If we call this up the ramp tension positive, then M1 tending to go up the ramp is positive. If M1 goes up the ramp, M2 will go down because they move together, right? So if M1 is going up the ramp, then M2 is going down. So if we call this tension positive, then down needs to be positive for M2. So for M2, we have M2G minus tension equals 0. And then we have two equations that we can work with. We can add them together. And why do we add them together? Well, that's because tension is set up to eliminate, which is good, because tension was not one of the given variables. Actually, let me just rewrite them one more time. We have T minus M1G sine theta, and I realized I didn't plug in for normal force. So that's mu s. That should be M1G cosine theta equals 0. And then here we have just M2G minus T equals 0. Add those two together. And what are we left with? We've got M2G minus M1G sine theta minus mu s M1G cosine theta equals 0. And what are we solving for? Find the minimum value of M2 such the masses will begin to move. So we're solving for M2. So we move all that over. G cancels out. We get M2 equals M1 we could factor out the M1 or not, it doesn't really matter. Sine theta minus mu s cosine theta. Woo! Intense. Alright, let's just carry on. One more example now. Oh, it's the same problem. Now let M1 equal 1.5 kilos, M2 equal 2.3 kilos, and theta equal 41 degrees. For what coefficient of friction would the masses be able to move at constant velocity once they were given a push? So once they're given a push, that means now we're finding mu k. Okay. Alright, but with mu k, it's the same equation. It's just, we can take this, except we're plugging in for mu k. We're plugging in mu k instead of mu s, so arriving at the same result. But then we're solving for mu k. G again will cancel out. So if we move that over, then we have m2 minus m1 sine theta equals mu k m1 cosine theta. So we divide m1 cosine theta, and this is our expression for mu k. Oh, but we're given numbers. Whoops. So then we could plug those in. To then get a value for mu k. 1.16, which is actually really high. So, well, oh well. It is what it is. It makes sense because if M2 has more mass, then the system would tend to accelerate this way, even if M1 was hanging straight down. And if M1's on the ramp, that'll take away some of its downward force. So, anyway, maybe if I switch the masses, you get a more realistic value for the coefficient of friction.